Okay, now in section 5.3.22, the question states that for a parallel structure of identical components, the system can succeed if at least one of the components succeeds. Assume that components fail independently of each other and that each component has a 0.27 probability of failure. We're going to complete parts A through C. Now, in part A, it says, would it be unusual to observe one component fail and then two components? Well, again, an unusual event is an event that has a low probability of occurring. And recall that an event with a probability of less than 0.05 or 5% is typically considered unusual. Now, to determine whether it would be unusual to observe one component fail, we're going to identify the probability that one component fails, and up here it's given us 0.27. So the probability that one component fails is 0.27. Therefore, it would not be unusual to observe one component fail, since the probability that one component fails is greater than the 0.05. Now we want to be able to determine whether it would be unusual to observe two components fail, and we're going to identify the probability that two components fail. So, because the multiplication rule for independent events state that the following E and F are independent events, then we would find the probability of E and F. And so the probability of E and F is the probability of event E times the probability of event F. So the probability of two components fail is equal to the probability that the first fails times the probability that the second fails. And since they're independent events, and we know that the probability that the component fails is 0.27, if we multiply them together, then we get 0.0729. So, therefore, we can say that 0.0729 is greater than 0.05, which is that 5% rule. So we can say that it would not be unusual to observe two components fail. Now, the next question states that what is the probability that a parallel structure with two identical components will succeed? So, the complement rule states that if event E represents any event and the complement of that is given by the formula below, we would take 1 and minus the probability of event E. Now, going back to the question, it says a parallel structure with two identical components will succeed if at least one of the components succeeds. Since the complement of at least one component succeeding is two components fail, the probability that a parallel structure with two identical components will succeed can be calculated by using the complement rule and calculating 1 minus the probability of two components failing. So going back to the first part, the probability of two components failing was 0.0729. And then we're going to use that information to calculate the probability that at least one component succeeds. So therefore, the probability of at least one component succeeding is equal to 1 minus the probability of two components failing. So we're going to take 1 and subtract 0.0729, and therefore the answer is going to be 0.9271. So the probability that a parallel structure with two identical components will succeed is 0.9271. Now in part C, the question stating how many components would be needed in the structure so that the probability of the system will succeed is greater than 0.9999. So again, the multiplication rule for n independent events states that if the events E subscript 1 or event 2 and so forth are independent, then we're going to use the multiplication rule. Okay, now recall that the system will succeed if at least one of the components succeeds. So we're going to let n represent the number of components in the system. So in order to do that, we would see that the expression that represents the probability that the system will succeed is 1 minus the probability of event 1 times probability of event 2, and so forth. And therefore, the number of components needed so that the probability the system will succeed is greater than 0.9999 is the smallest value of n that makes this formula greater than 0.9999. Now, recall that from part A that each component has a 0.27 probability of failure. So therefore, it would be 1 minus 0.27 to the nth power. Now, while the smallest value of n that makes that formula greater than 0.9999 could be found using algebra or trial and error, for the purpose of this explanation, trial and error will be used. So recall from part B that the probability that a parallel structure with two identical components will succeed is 0.9271. This probability is not greater than 0.9999. So what we would do is we would need more than two components. And so we're going to calculate the probability that the system will succeed with 3 components. So if we try the probability that the system succeeds is equal to 1 minus 0.27 to the third power using 3 components, gives us 0.980317. Again, this probability is not greater than 0.9999. Therefore, more than 3 components are needed. So we would have to keep finding the probability the system with one additional component succeeds until the probability that the system succeeds for a given number of components that's greater than 0.9999. So what we'd have to do is we'd have to try this as many times as we can to see how far we can get to a number that's greater than 0.9999. So if look at this table here, 1 minus 0.27 squared gave us 0.9271. Okay, this number that we get there is less than 0.9999. Okay, if we plug in 1 minus 0.27 to the third power, which is what we got over here, again, this number is 0.9999, is less than 0.9999. Okay, if we take a look at 1 minus 0.27 to the fourth power, again, that number is less than 0.9999. Okay, 1 minus 0.27 to the fifth power, again, is less than 0.9999. If we look at 1 minus 0.27 to the sixth power, again, this number is less than 0.9999. If we look at 1 minus 0.27 to the seventh power, again, this number is still less than 0.9999. Once we get to 1 minus 0.27 to the eighth power, we can see that this number is actually greater than 0.9999. So therefore, the number of components that would be needed in the structure so that the probability that the system will succeed is greater than 0.9999 is the value of 8.